Yes. So the last lecture for today will be about machine learning for signal background discrimination in high energy physics from Denise Klekots, who is a student and he is an engineer of the nuclear physics laboratory at Taras Shevchenko National University. And now I stop presenting my slide, and you can try sharing your screen and start your presentation when you're ready, Denise.
Okay, can you please confirm that you can hear me and see my slides?
Yes, everything is great.
Okay. Hello, my name is Denise. As already was told, today we will talk about how we can use machine learning in high energy physics for discrimination between signal events which we interested in and a background event which we want to reject. And for that example, I will show that on an example of my own work, just to have something in hand. Here is my contacts if you want to contact me for some reason. Okay, let's start from the general view of particle physics or high energy physics, which, for now, most complete model of all the physics is the standard model, which was already introduced yesterday. And just to say a few words about that, it has 6 quarks, 3 charged leptons, and 3 types of neutrino. Also, it has 4 gauge boson, which is correspond to each interaction. Let's say gluon correspond to strong interaction, as we know, which is binding together nuclear in the atoms. Photon correspond to electromagnetic interaction. It's mostly used by humanity type of interaction, and U and double W bosons are used. They correspond to weak interaction, which is in our world, it corresponds to some type of the radiation decay. Special place is for Higgs boson. But basically, I want to talk a little bit more what we are as high energy physicists study. The reason is that this model is not complete. We know very well that there is something that cannot be described by this model. So we must to do something with it, to add something to this model or so on. And for that reason, the search is ongoing to find new physics. Basically, such type of new physics very well is, there is researches on the collider experiment for new physics. And today we will speak about how we can use machine learning in that area of physics. But for today, for now, let's take a few slides on introduction, what is colliders and so on, to better understand what will be in the next slides. Okay, most of you probably know this Large Hadron Collider, which is really large, and which is Hadron Collider located in Geneva, and it has 4 experiments: LHCb, Atlas, CMS, and Alice. Basically, the new particles which we want to discover are created in the process when we collide well-known existing particles with each other with very, very huge energies. And such type of new particles, they are usually very, very short-lived and quickly decay in some other particles. And basically, we reconstruct that new particles by the product of their decay. And here is how we do it. Okay, this is just a very, very quick scheme of the transverse cross-section of the place where is everything is happening. Okay, let's suppose we have some particles. I plot it here with the green color, which is decay, and these green lines is tracks of the products of the decay of the particle. We can measure their properties at the detector, which is located at the in some distance from the place where the particles is created. But the problem is that there is very, very large interaction in a second. Okay, we have, if we speak about Large Hadron Collider, there is about 10 to 11 particles in each bunch, which is colliding with frequency once per 25 nanosecond. It's very, very, very large number of interaction, and it is very possible that some particles, let's say we are interested, let's say, in discovery of Higgs boson. Why not? We know which particles must, which particle we want to expect as the products of its decay. But it is possible that another particles, which we not interested in, but they can be aligned in such a way that detector measure it pretty much the same, like if it is some particle. It's what we do not want to have, because it is create a background. Okay, we see some candidate which is look pretty much like our particle, but it is not. It's called combinatorial background, and it is a big issue in the such type of experiments. And what basically we want to do, we want to clear it out as much as possible. But it's done this process done on the stage of data analysis from that data which was measured from the detector, which is located in the point where the beams collided with very, very large energies. And basically what we measure tracks of the particles, which is decay product of our new particle. And here is some visualization how it can look like. You can see it's a vast majority of particles, and we can measure them inside in the detector, which is some place off from the interaction point. And basically what detectors and our systems do, it's measure properties of these tracks. Let's say heat, I mean the position where this particle was, where this product decay hit the detector, time at which it was momentum of the tracks, and so on. Also, there is a good job how to identify particles, because if some particles hit the detector, we usually want to know which particle it is. Let's say proton or electrons or gamma quanta, it's a different type of particle. And some other parameters are reconstructed as well, such as position where the particles was created and where the particles decay, its lifetime, and so on. In the result of that, we have events, and we have properties of each tracks in that event. Event, it's let's say decay of one new particle, let's say Higgs boson, and at the end of this pre-processing, we have properties of each product of that decay. Some of them measured very good, some of them not so, but we have it, and it comes to now we came to the stage of the further analysis. How we can do that, and that analysis we can also do with machine learning. But for now, let's talk about a little bit more about the mass spectrum. What is it? Okay, most of you know this good scientist, Albert Einstein, and his famous equation E equal m c squared, which gives us a link between energy and the mass of the particle. It widely used in high energy physics because mass of the particle, it's like a passport of of particles. Basically, what we want to know the most, it's mass of the particle. And if we have some candidate which look like a particle, we can reconstruct okay, having energy of product decay and knowing which particles that is due to particle identification, we know their mass, and having energy and the mass of the decay product, we can reconstruct mass of the primary particle. And usually, if we interested in some particle, we know about which range it must be, and we can just plot it in so-called mass spectrum. And what we expect that in the position where is the mass our particle of interest, there must be peak. And you can see from the left and from the right, and under this peak, it's combinatorial background, which is also included in this spectrum, and we do not want it to be, but it is. And what can we do to clear the spectrum? I mean, to decrease the combinatorial background. The simplest approach, we can put a cut on some variable. Let's say if we have some particle which is comparatively long-lived, we can put a cut on its time of life. And just reject all particles which have which lived less, and due to this, we reject large fraction of the background and maybe some signal as well. Well, this approach works very good, but it's not always enough to put simple cuts to clear our spectrum. So we need to invent something more difficult, let's say, some huge equations with with some combination of the parameters of the tracks, and well, it is a good brain job, but it's not always obvious how to do that. Much more easier it's to just train machine learning, because the let's say we must to invent some difficult equation to put some cut on multivariable on something which include many variables, but we not always know this equation. But instead of knowing equation, we can just train machine learning some algorithm which will work pretty much the same, and it is very fine. It well, it really good. It do a good job, and it's spare us lots of time how to do that. And for that, we need simple machine learning model, which is binary classification, which is give us output, let's say a binary output, saying, okay, this particles, this event probably background, or this event most likely signal. And Why not? But the problem came as all of you know that machine learning need to have some data on which we can train our model. And where do we take this data? This is a good question. Okay, what we need? We need some some data with labels. We need some data from the background for which we know that it is really background and there is no signal. And we need some data for the signal for which we know that it is really signal and there is no background. Okay, simplest way maybe it's just to simulate. A Monte Carlo to make some Monte Carlo simulation, let's say on signal data, it works fine. Because we know some theoretical prediction of how it can be. We know the standard model, we can calculate interaction and we can predict how the particle will decay. And after that, having some large simulation framework which simulate how the particles interacts with the matter, how the detector react on this interaction and which output from the detector we have, we can just simulate it well. And it is very fine, and actually not very fine. There is some, it's not a perfect, it's good, but not perfect. But we know that we have particles and they must likely look like our signal particles. But simulate a background, it's a very big deal and it's not so easy because we do not even know all type of interaction which can be inside the combinatorial background and so on. So it's just probably more easier to take this data, which we know that it is probably most likely background from somewhere. And let's take a look at this mass spectrum. Okay, here is we know this peak. We know that most likely it have some signals. But if we look at some data here with larger mass, we know there is no signal here because this particle, in this case, let's say lambda sub c plus, cannot decay in the product which have larger mass than primary particle. So obviously this here area is clear background with no signal. So let's just take it as our background for training machine learning. So we solve a problem. We have labeled data for signal, which is from Monte Carlo simulation, and we have labeled data for background, which is a combinatorial background which we measured and for which we're confident there is no signal in that area. Okay, what can we do next? First of all, we must select our features, which is some properties of the tracks, which will be used by the our machine learning model. And we must be very confident that neither of these features correlate with the mass of the particle, because if it is correlate with the mass of the our primary particles, the model will quickly train in such a way that it just cut a window in this area and it will be no use for us. It will not clear background. Okay, to do such type of check, it's not very difficult really, but what more bad for us that we have, let's say, signal background signal samples, which is correspond to decay of the simulated particle, which is in mass which have mass close to, let's say, this peak, and we have background which is completely different mass region. It's not very nice, but as well as neither of input parameters correlate with the mass, it seems to be fine. as well, I have to mention that these Monte Carlo simulated signals they not perfect, because there can be some processes inside the collider which cannot be included in the simulation, but it is not critical. We can survive with it. And after that, we need to have our machine learning model. We can choose what we like as far as it is work good, and it must be binary output. We can try let's say neural network, or we can try boosted decision tree, or some let's say decision tree, and we can try whatsoever. But again, we need to be sure that at each layer of this neural network, or at each node of this decision tree, output of that layer or of that node do not correlate with the mass, because otherwise it will be model will be overtrained to cut a window in the peak region, and its output will be useless. And again, this model which we use, it not must be too large. If we have, let's say, neural network, 1 or 2 hidden layers will be completely enough. Because in case of large model, we as a physicist not always can understood what it doing, and it is real danger of overfitting, which we do not want very much. Okay, the next thing that we have a data, Monte Carlo simulated data for signal on which we train our model. Well, it's let's say it's nice, but not too much, because we also need our Monte Carlo simulated events in the future to estimate how good our model reject background. And after all, at the end, we need to put our Monte Carlo data for prediction to our model. And if we train our model on that data, obviously we cannot correctly put this data on a prediction to our model, because it always result will be perfect, because model was trained on the data. Well, what can help us? We can use so-called k-folding. Let's say we split our training data set on two parts, equal parts, and instead of one model, we have two models, and we do the following. First model we train on the first half of the dataset, and second model we train on the second half of the dataset. But if we want to predict some event from the first half of the dataset, we use second model. And if we want to predict some event from the second half of the dataset, we use first model. So in this way, we never predict, model will never predict data on which it was trained. It's very fine. K-folding of 2 can solve our problem. So let's move on basically to what I did in my work, because I don't remember if I mentioned that I doing my master thesis on data analysis with in high energy physics, and actually I doing now what I described to you. And what I did, I have a choice between neural network and boosted decision tree, but I do some test, and performance of boosted decision tree in this case was really much better than neural network. So my choice was obviously to the boosted decision tree, and in my case I use 15 parameters, which is 15 15 parameters of the track to model they was used for training and they will be used for prediction. And as you know, boosted decision trees have several instance of trees. In my case, it was 1,000, and max depth of each tree was six, let's say, levels. And yes, I already mentioned that I tried to do the same with a neural network, but performance was much worse. And let's have a look at the metrics at which we evaluate our model. Is it good or is it can be better? Okay, what I want to describe here is true positive events. It event which was really a signal and was classified like a signal. False negative events, events which was in reality signal, but it was classified like a background. True negatives, it's an event which in reality was background but was classified as a signal. And false positives, that events which in reality was background but was classified as a signal. And for our to evaluate how our model is, we use true positive rate. It just to calculate true positive rate, we need this number of true positive classification divided by sum of true positive and false negative ones. And second matrix which I used was false positive rate. And here we have validation of our model. Let's have a look on the left plot. It describes so-called receiver operator curve, which was in use since World War II, if I don't mistake, and primarily it was used for evaluation of how good our radar is. Basically, these curves give us understanding how our model good. If it is, let's say, more to the top, it's better. If we have a model which randomly give us signal or background, it will be straight line like this dashed line. And as a characteristic, I use area under this curve. A maximum it 1, it's perfect model, and if model random, it will be half of unit. In my case, it's 0.99. It's very good result. Okay, true positive rate in on the y axis and false positive rate on the x-axis. This is parametrical plot for, let's say, one point here is selected on this curve, selected for one threshold of our model. And basically for threshold, we can see this right histogram, which is okay, it is a histogram, and on the x-axis, it's what our model give us on the prediction on our validation set. And we can see that a larger number correspond to signal, and lower is correspond to background. If we have a threshold 0, we just reject all which is for which output is less than 0. And for different threshold is the true positive rate and false positive rate is calculated, and this receiver operator curves is built. Okay, but 0.99 is very good number as for a model. And second, what we need to do is to do cross check. Is really our model do not cut a window in the area where the peak must be. For that, we have here our mass spectrum, let's say, which have a bins, and let's say in this bin we have about 30 events. Okay, we can calculate on our validation that, of course, calculate how much calculate output of the our model for that bin and take mean value of that and plot it in this picture. If we have a flat line here, it means that our model do not prioritize some events based on their mass, and it is the case here. It is fine. We have some fluctuation, but no, the model do not give larger output value for event which is closer to resonance mass, and the same for background. It does not change very much on the mass except of some fluctuation. It's fine. We always must to do this cross check to be sure that our model do not cut our data in such a way that we have peak of the event which is not signal. Okay, just we need to be sure that our trained model does not trick us. Okay, in my case, I'm sure I'm fine. Let's go on. The second is to select the best threshold of our model. Okay, from here we can see that probably the best one is 0. Well, on validation data, of course, but on real data, it's not always the case. And what we can do, we can just to scan our threshold, let's say from 0 to 16, to select the better value of some matrix. And which matrix we want? Okay. Of course, we want to have as much signal as possible and as little background as possible. But it's not always possible, let's say. In some case, we can have 0 background and very little signal, or in another case we can save all the signal but also save the very good portion of the background. We want to avoid both of that situation, and for this we use a matrix called statistical significance, which is a number of signal events divided by number of signal events by sum of number of signal events and background events. And actually, how we find out how much signal and background we have? Well, it's easy. We have mass spectrum. We just fit that data with a peak, let's say Gaussian peak, and linear background. And area of this peak correspond to number of background of signal events, and area of background, let's say here under this peak, we correspond to number of background events. And after that, we can just change a threshold of our model, pass all our data measured to the model, and it gives us output for we can by changing threshold we can scan which for which threshold there will be most larger statistical significant, and choose this one, in this case 10. It seems fine as our threshold of the model. Okay, after that we done everything. We have model, we train it, we validate it, we check that it does not trick us, that it do not coherent with the mass of the particle, of the new particle or particle which we study. Okay, we have everything. After that, we just do background cleaning. We just, to have a complete model, we take all our measured data. We have 15 parameters of the tracks for which our model was trained and which is used for prediction. We pass all the data through the model. We have predicted value. We have a cut of the model output threshold. We reject all that do not satisfy threshold requirements and accept all that do. Okay, this approach very significant improve our data. It's really clear very large portion of the background, combinatorial background, I mean, and it's unfortunately it also reject some good signal events, but we cannot help it. But it reject background much more than a signal event, so we have some signal events saved and background cleared. Okay. After that, we can do further analysis of our data. And here I just want to show you what I used in my work in my master thesis. Here is how the mass spectrum looks without machine learning. It's pretty, let's say, ugly. We have some peak here, but it's hard to even distinguish, is it really a peak or is it some fluctuation? But after we apply to this our machine learning, we have voila, nice peak. But the problem is that you can see here we have 800 events, and here only 100. So we clear background and events as well, but obviously we clear more backgrounds than events. Okay, here is all what I want to show you. If you have any question, please ask. I will be happy to answer. Indeed, I'm eager to hear your questions.
Yes, thank you for a great lecture. And now give me 1 minute. I'll show my screen.
Okay, shall I stop sharing mine? No,
no, it's not needed.
Okay.
So you see my screen with questions, I hope. And the first question to you, what are the key ML models commonly used for signal background discrimination? And how do they compare in terms of accuracy, efficiency, scalability?
Okay, that's a really great question. As I know from my work, there is not such common model like we have, let's say, for computer vision. For computer vision, we have very good established models such as ResNet, YOLO, and so on. And we have metrics for them. But if we speak about this type of work, it's, let's say, state of the art. I know that all of that models are not very complicated. It's only 1 or 2 hidden layers. The number of parameters, or features, it's also not very large. Let's say 10, 20 or so. And probably for each analysis we have we train a different model, because in my analysis we have some types of features which is track parameters which is very good for discrimination signal background in this mode. In another it might not work. So basically, as for me, as far as I know, it commonly for each analysis we have different model, and there are no common used model for that.
Okay, thank you. The next question is how to address issues of class imbalance and limited label data when training ML models for signal background discrimination in high energy physics.
Okay. it's really good question about if we speak about class balance. For that, we clearly must to select our training data set in such a way that number of background or number of signal events will be equal. Otherwise, our model will be biased and it is not very good. If we do not have enough signal events, we can just have Monte Carlo simulation and simulate more. It's not a problem. But if we do not have enough, okay, well, it's not a case when we do not have enough background data, because background we measure from real data, and there is always plenty of background, believe me.
Okay, thank you for the answer. And the next one, this approach applies for particles with mass, right? How massless particles are detected then? And the author mentioned that he or she is a non-physicist.
Okay, that very good question. If we have massless particles, let's say gamma quanta, which is not have a mass, but it have energy. In terms of that, we can, let's say, broadcast that okay, on the mass spectrum which I showed you. I showed mass, and it was in units of energy. It was GeV or MV, something like this. And by this equation of Einstein, we really know that mass and energy is mostly the same. So if we say about massless particles, we discuss not its mass actually as it is, but its energy, which is also can be plot on this type of mass spectrum. And to detect energy, we have special type of detectors inside in high energy physics, which is calorimeter, which okay, if we have here is, let's say, calorimeter, here gamma quanta, which hit calorimeter, it deposit all its energy, I mean all energy of gamma quanta inside the calorimeter, and calorimeter measure how much energy it was, and basically this energy, it will be, let's say, the same as the mass for this gamma quanta.
Okay, good. And the last question is the implementation available on GitHub or maybe
Okay,
some other repository?
If you speak about this, my code which I developed, unfortunately not, because I work on the collaboration data of LHCb collaboration, which is I'm not eligible to share with you unless it will be officially published by the LHCb collaboration. And of course, I have a not GitHub, but GitLab repository for that, but I cannot open it to the public. I'm sorry.
Okay, I see. So then I stop sharing these questions. Thank you for the lecture. It was very interesting.
Thank you too.
And I hope that all of our participants liked this lecture too.
Well, have a nice evening.
Yes, you too. Thank you all participants for joining our lectures today. Hope you learned something interesting for you. See you tomorrow.